Good morning, everyone. Welcome to my talk. It's my pleasure to be here to share our research on program modularization. Today's software systems are fast bloating and monolithic. They tend to have millions of lines of code in unsafe programming languages. And they may have thousands of modules, and there's no internal isolation between these modules. And these modules are not equally trusted. Some could be less trusted and buggier. And this results in some security issues. Each year, we can find thousands of critical vulnerabilities, and a single vulnerability may compromise the whole system, whole program. And also, we can witness hundreds of exploits each year, and most of these exploits are actually memory attacks. So this work was motivated by a question. How do existing memory attacks work? There is a pattern. Typically, attackers would exploit a vulnerability in one module to compromise other modules by manipulating their data or accessing their code. So intuitively, if we can block this kind of invalid cross-module access, we can prevent this kind of memory attacks, right? And a general solution to this kind of protection is called program modularization. Its idea is to determine which modules are independent from each other so that we can separate these modules. And the key technique to realizing this kind of protection is called dependence analysis, which has been considered infeasible for complex programs, complex C and C++ programs. And the major reason is that they typically employ traditional data flow analysis, which suffers from some well-known issues, such as massive false aliases, the path explosion problem, and unknown in-record targets. So we haven't seen practical defense mechanisms built on top of this kind of dependence analysis. So in this work, we propose a novel concept called type-based dependence analysis. Its goal is to determine which modules can never pass a type of data to a target module, or may pass a type of data to the target module. And here we define a module as a compilation unit, such as a C file or a C++ file. Okay? And this concept was proposed based on an observation. We found that determining dependencies of a specific type is actually much more practical and can be still useful. And the reason is that the interfaces of modules are actually well defined with type information. In fact, there are only two data flow channels between modules to pass data. How can one module pass data to another module? There are only two ways. First, they can make a function call. A module can make a function call and pass the data through the function argument. Or one module can store the data to a global variable first, and the other module can load the data from the global variable. So just the two ways, function arguments or global variables. So, and both channels come with type information. So by inspecting these two channels, we can know which type of data flows can happen between two modules. So that's why this can be practical. And here is an illustrating example. We have global variable G, we have module M1 and the module M2. And there are three cases. In the first case, M1 makes a function call and pass the object P through the function argument. So bar is a function of M2. In the second case, M1 first stores the data to the global variable G, and then M2 loads the data from the global variable G. And then the last case is a combination of function call, and the global variable. So in all these cases, there are only two ways to pass the data, function call or global variable. And we can easily get the type information of P by analyzing the function call and the global variable. Okay? So the high-level idea of typing is to first employ type-based analysis to figure out the possible types of data flows between two adjacent modules. And then we transitively identify dependent modules of a given type and a given module. So the input is a pair of type and the module, the target type and target module. So this kind of analysis is type-based analysis. It's not data flow analysis. So it wouldn't suffer from the traditional issues with data flow analysis. Well, the idea is intuitive. There are some technical challenges. Obviously, there are so many typecasts in C programs. We have to carefully handle the typecasting. When we analyze the function argument, for example, if it's type A, right, we need to consider if type A has been casted to or casted from other types, and we need to consider these types. So we carefully analyze typecasting instructions and operators to comprehensively collect these casted to and casted from types for each module. Second, objects can be really complicated. A field of a struct can point to other structs and recursively. So we also have to carefully recover these kind of nested types. And also type itself doesn't include the direction of the data flow. So we also need to recover the flow direction of types. And we perform the type flow analysis. And typing requires to know the targets of individual calls, which is unknown by default. So we also need to figure out individual call targets, and I will talk about how we do that later. Right, and after addressing these technical challenges, we also made an optimization called type elevation to significantly improve the precision. Here we have an example. We want to perform the dependence analysis for the function pointer get policy. However, as you can see, the function pointer is passed in together with its parent structs, VMA and VMOPS. So in this case, we can also apply the dependence analysis for its parent structs, VMA and the VMOPS. So the final results will be much more precise. However, we need to note that this kind of analysis requires that the structs are not internally created. They must be passed in from other modules. So we also need to perform so-called externality analysis. Some important implementation considerations, as you may know, LVM has switched to opaque pointers where the type information of pointers are not immediately available. Okay, so in this implementation, we use the older version where opaque pointers are not enabled. However, it's possible to make it compatible with opaque pointers because we can get the type information of pointers by looking into the metadata and the debug information. Second, we need to frequently compare types, which is not easy because the type of fields of structs has lots of noises. So here, to be conservative, we just use the name of the structs for the comparison. Similarly, for union types, there are some implicit typecasting, so we also just use the name of union types for the comparison. We have two interesting applications of typing. First, we use typing to resolve individual call targets. And the motivation is that existing solutions which use type-based analysis to globally match targets of individual calls. So our motivation is that why don't we just match the targets within dependent modules instead of the whole program? This way we can improve the precision. So in this work, we apply typing to first identify dependent modules for individual call, and then match the targets of the individual call just within these dependent modules to improve the precision. And the precision evaluation is actually good. You can see, compared to the traditional, the state-of-the-art, Type-N can additionally remove more than 30% of targets for individual cores. And the analysis time is actually small. For a large Linux kernel, it takes only 8 minutes to finish the analysis. And we indeed observed some false negatives, but it's not about the approach itself. And causes include some special coding style in a targeted program. For example, Linux may have intentional out-of-band access. And LVM type system may have some issues, and of course, Type-N itself has some implementation issues. In the second application, we apply Type-N to protect critical data structures in the Linux kernel. We first manually identify types of critical data structures, the ones involving capabilities and permissions, and then we apply Type-N to identify the dependent modules of these kind of critical data structures. We found that actually 99.9% of modules will never write to this kind of critical data structures, so they can be safely isolated. This way we can protect these data structures. To conclude, type-based dependence analysis is practical and still useful, and a major observation is that there are only two well-defined data flow channels between modules, and both channels come with type information. And Type-N is a basic static analysis technique. It can enable multiple security applications such as I-core analysis, inter-core analysis, program compartmentalization, and software deploying. And in the end, I'd like to thank my department. We have a very, very supportive department. Last year, we have a teaching release, so I didn't need to teach. So I had some time to work on this project myself. And without their support, this project wouldn't be possible. Thank you. With that, I'd like to take your questions.
Thank you very much. If you have a question, please come forward. So you mentioned false negative in your analysis. So what is the practical impact of having a false negative?
Yeah, so we can use these analysis techniques for scenarios where false negative can be tolerated, such as bug finding, vulnerability analysis, exploitability analysis. But if we want to apply this technique for defense mechanisms where runtime errors are not acceptable, so we need to be careful, and we need to figure out these false negatives and solve them. Yeah.
Okay. Thank you.
Hello, very nice talk. I have an open question maybe. Since we know that you just mentioned after the LVM 15, we don't have the type information in the bit code, and the reason is that because the developers think the type is not accurate. So I just wonder, in the future, after that, so how can we perform some type-related static analysis if we without those type information? Just an open question.
Mm-hmm. So this is a good question, first of all. There could be two possibilities. First, there are some APIs provided by LVM. You may use these APIs to gather some type of information for some cases, but it may not be comprehensive. Second, a more practical way is actually, as I mentioned, you can use the debug information or the metadata. They are actually available in the metadata. So you can look up this metadata to get the type of information of pointers.
Nice work. I had a couple of questions about the for weakly typed programming languages. First question is that what if you have some code that's just serializing or deserializing data? So how would that system work on that code?
What do you mean by serializing?
Basically just you give it some data and it basically serializes the data in a blob so that it can be transferred to different across modules.
Yeah, so first of all, we have to assume all the code is in the analysis scope. But if all the code is in the analysis scope, then our observation will still hold. You have to pass the data through function arguments or global variables, and by analyzing the space, the interface, you can still figure out the possible types of data flow. But if something is out of the scope, for example, you perform some data flow parsing out of the analysis scope, then we have to take that as a separate module, and sometimes we need to model these external behaviors. Yeah. And for this weakly typed system, so as long as typecasting exists, by analyzing the typecasting, we can still figure out the possible types. Yeah. Not sure if I answered your question, and I'm happy to discuss further with you offline. Yeah.
And yeah, that's pretty much it. I'll talk offline.
Thank you.
Okay, thank you very much. Let's thank the speaker again.